Not every soil is a natural deposit. For example, you can have artificial fills, embankments, levees, earth structures, such as reinforced earth walls, etc. So these are, let's say, engineered deposits. And if you are engineering your soil, you would like to improve its engineering problems as well. So those are flow related, deformation related, and strength related problems. So uh, for this purpose, what we do is we compact the soil. So when you compact soil, you densify it. By reducing air volume. By application of let's say energy or effort in the form of static or dynamic loads. So when you densify a soil, when you reduce its void ratio, it becomes less permeable, it becomes less deformable, and it becomes stronger. We are going to cover those engineering properties later, but just out of common sense, you can imagine this, I believe. So if we are building something, and usually such engineered soils, earth structures, they are very large volumes. So imagine the body of a dam, for example, body of an earth embankment dam, or the fill under a highway. You are talking about perhaps millions of cubic meters of soil. So it really becomes financially important to make this process more efficient. And for this purpose, we investigate compaction characteristics of soils. So the quickest way of doing that is by looking at how compaction properties change with water content. This is called the compaction curve. And basically, on one axis you have the water content. On the other axis, you have a measure of how dense your soil is. And what we use is the dry density, or sometimes dry unit weight. The reason we don't use the bulk density is because the bulk density includes water, but water content can change. But what matters is how dense is the solid structure, solid skeleton of the soil. So what happens is, basically, at low water contents, let's say you have at this water content, for a given energy, for the same applied energy, you have this much you are able to compact with a certain energy, you are able to compact this to this density. If you increase the water content, water will act like a lubricant. It will make the soil grains, especially the finer grains, slide easier around each other. And uh, as your water content increases, your the density you are going to compact the soil with that energy also increases up to a certain point, beyond which you have added so much water that the water starts to get in the way, because it occupies volume as well. So the volume occupied by the water is not available for your compaction anymore. So if you have too much water, then you can't compact it as effectively. So this gives you a compaction curve like this. For a unique or given energy or effort. So what you have here is called the optimum water content. And what corresponds to that is the maximum dry density. So what what people do is, generally in the field, you get your soil that you are going to build with, and then you determine its compaction properties like this, and then you try to mix it with this much water so that your compaction is the most efficient. So of course, if you apply greater energy, you get greater dry density, so you will get a higher curve. If you apply lower energy, you will get a lower curve. But the optimum water content for different energy levels, yeah, it changes a bit, but it doesn't change too much. And the way in practice people express the densities of fills is in terms of percentage of raw dry max. So you can say 98% compacted. So that means 0.98 times this dry density, the maximum dry density, is your required dry density for that fill. And obviously, because you can have even greater densities with greater energy, the greater compaction efforts than this, that means you can have greater than 100% compaction, because you can keep compacting it more and more. Of course, up to a certain level where you cannot compact the solids anymore. Now here I'm going to also pair this with a phase diagram. So I have solids, I have water, I have air. And because I'm using water content as my axis, I'm going to start with this time, and I'm using density, so I'm going to start with mass, and mass of solids is 1, mass of water is W, mass of air is 0. So my volumes are going to be for the solids. It is going to be 1 is my mass divided by the density of solids. So GS raw water. And this portion, W, its volume is going to be W divided by raw water. And the air volume, or rather the void volume, is going to be this volume of water divided by degree of saturation, because degree of saturation is this divided by this volume. So this void volume is the this much. So from here, if you calculate the dry density, if it is dry, this weight of water is gone as well. So what you have is 1 for the mass, but all the denominators are going to have, let's first write the volumes. All the denominators are going to have the raw water in them. So let's put raw water up. Divided by the total volume. The total volume here, as you can see, is volume of solids 1 over GS plus volume of voids, which is water content over S. So here are my axes, raw, dry, in terms of my parameter, water content. Density of water doesn't change. Degree of saturation, yes, changes. GS for a given soil doesn't change. So for a given degree of saturation, let's say for fully saturated condition, for fully saturated, this is 1. So S doesn't change either. So if your soil is fully saturated, what curve is this? What type of function is this? Constant divided by constant plus W. Okay, constant plus W means just the axis of the W is shifted. So number divided by parameter. That gives you a hyperbola. So that gets you, let's say, this. So this is your, for S is equal to 1. If you change the degree of saturation for, but again, draw a constant degree of saturation curve, let's say instead of 1, it is 0.9, you get, again, a hyperbola, but another hyperbola. So you can have, I'm arbitrarily drawing this, by the way. There's no rule about the location of this peak versus degree of saturation. But anyway, so you can have something like this for S is equal to 0.9. Oh, sorry about this pad is no good. And then if you can keep doing that, you can keep adding more hyperbolas into this picture. So this is for another S is equal to 0.8. So, well, that's not visible. and so on. So what's important here is no matter how much effort you spend, so for example, I spend a larger effort, your soil can never be more than fully saturated. So you can never go beyond this line. And different curves might go around following the same lines basically. So your peak, if it is here, then it might also be close to there. Anyway, so if you apply more effort, you can get a greater density at a slightly lower water content, at a slightly lower degree of optimum water content. But the change in water content is generally small, and in the field, your control over the water content isn't precise anyway. So people usually don't consider this effect that much. Still, if you know that you need a very dense field, you are going to require a large density, so you are going to apply a very large effort, then you should be determining your compaction curve with a large effort as well. So you should, when you are measuring or determining your compaction curve, you should consider this. You should keep in mind how much effort your final design is going to require. So if you are doing a regular fill, maybe under a highway, then yeah, you can look at the lower effort one. But if you are doing a fill for an airstrip or something like that, then you might want to look at the greater effort. So, okay, that is the concept. And the remaining bit is how to determine that. So for that purpose, we have some standardized compaction tests. And the one that's most commonly used and that we are going to cover also in the lab sessions is the Proctor compaction test. So to make a standardized compaction test, because you are after a curve that is for a given specific energy, what you need is to standardize the energy applied per quantity of soil. So in this particular test, what you have is a mold that is about 10 centimeter by 10 centimeter. So it's the cylindrical mold. And into this, what you do is you drop a hammer that is 2.5 kilograms, about 2.5 kilograms, from a height of 30 centimeters. So this is 10 centimeter, or rather it's 4-inch mold. And this is 1 foot high actually. So So you do this onto your soil 25 times, 25 blows on each of three soil layers. And of course, this also has its own standards. So this is 5 centimeters. So it's basically half of your container and distributed evenly. Let's also add, so you don't always hit the same place. You keep changing your location and try to hit everywhere. Uh, and of course, there are, again, because it's a standardized process, for example, British standard says do this with 27 blows instead of 25 for some reason. But anyway, it doesn't change significantly. Uh, and in your soil, you can have no grains larger than 9.5 millimeters is allowed. And this is actually uh, going to be a recurring theme in laboratory tests that are that have a defined geometry, that have a specimen with a defined geometry. So your grains cannot be larger than something like 1/10 to at most like 1/6 the smallest dimension uh, of your specimen. So, or use a 6-inch mold, 15 centimeter mold, and 56 blows per layer, because if you increase the diameter by 1.5 times, your area, therefore your amount of soil increases by 2.25 times, 1.5 squared. So 2.25 times 25 is 56. To include up to 19 millimeter grains. So if you have larger grains, you can use a larger mold. That is kind of straightforward. But then, what if you have just a few grains larger than these limits? Then there are ways to get rid of them and correct your results. So if you have some large grains, some depends from standard to standard again, but say less than about 25-30%. So if your soil has some grains larger than 19 millimeters, but they are less than 25%, you can sieve them out. But then apply corrections to both water content and dry density axis of the curve or of your results. So why is that? Because basically in your lab you have a bunch of smaller grains plus air plus water, but in reality, if you haven't sieved them out, then you would have, instead of those, you would have a single solid big grain. So some parts of your volume would have, in reality, it would have nothing but solid, but in the lab you are having voids as well and water as well. So you are changing both the water content and the dry density by removing large grains. So you have to correct for that. So the lab handout for the compaction test, for the Proctor compaction test, will include the formulas for the corrections here, and you can actually devise them again by volumes, masses, and density calculations. Anyway, I'm not going to rewrite them here. They are going to be in the handout. So and of course they are in the ASTM and other standards as well. So another thing you need to consider is, as I said, you can sometimes test with an increased effort. So this is the standard effort. So if you have modified effort version, increased effort version, then instead of 2.5 kilogram hammer, you use a 4.5 kilogram hammer or 10-pound hammer, and instead of 1 foot, you drop it from 1.5 feet, and instead of 3 soil layers, you make 5 soil layers. So there is a larger hammer that is able to drop from a greater height. By the way, the height is standardized by having a tube through which the hammer is able to fall. So anyway, that means there is a bigger hammer, but some people mistakenly assume if you use the bigger hammer, you should use the big mold, or big mold, big hammer. No, there is no rule like that. You can use the small hammer, so standard effort with the 4-inch or 6-inch mold, or you can use the larger hammer, modified effort hammer, with either 4-inch or 6-inch mold. They are all possible combinations. It just depends on what grain sizes you have and what effort you want to apply. Okay, actually, for the sake of completeness, let me quickly include the correction formulas here as well. So the corrected dry density is going to be measured, or the dry density obtained from the test times GS of the coarse fraction times density of water, divide that by flow dry test, times course fraction plus GS course density of water 1 minus course fraction. So if you look carefully, this part is the fine matrix and this part is the density of coarse solids. So here, let me say C is coarse fraction that you removed. By the way, ASTM standard says if it is less than 5%, don't bother, don't remove it, and that would be too little an error to go through all this trouble. And, oh, not C, not G, sorry about that. C times water content of the coarse fraction, which you need to kind of assume because it is an imaginary water content that would belong to the coarse grains only if they were mixed together with the fines. Plus 1 plus C water content of the matrix soil. So this assume a small number like 1% or 2%, something like that. So again, this is your, in reality, your coarse grains would have this much water, your rest of your matrix would have this much water. By the way, when I say coarse fraction that you removed, it is not all coarse soils, it's not the general coarse fraction, it is the part above 9.5 millimeters or 19 millimeters, depending on which one you use. Or actually, some people do this by removing all the gravel. So some people just remove everything above 4.75 millimeters as well. That's it. So here there are a few additional steps I need to tell, because this basically, when you do this, what you do is you have your mold, you compact each layer, compact each layer evenly with the standard energy or effort. Then when you fill the mold, basically you get rid of the excess material and weigh the soil in the known volume of the mold. So the mold is some cylinder made of metal, so you can just measure its dimensions and determine the volume. Of course, in order to avoid spilling out soil, there actually is an additional color on top here. So you can compact through that. And then take water content sample, water content measurement from that. So it's not like you mix your soil with a certain water content and that is your water content, because you mixed it and then you put it into the mold and then you are compacting it. Through that time, some evaporation might also happen. So you want to take the final water content of the sample. And from this step, you can get the bulk density, and you should know that the dry density is going to be bulk density divided by 1 plus water, because you are in one of them your mass is just mass of solids, in the other one your mass is mass of solids plus mass of water, so the ratio is going to be as such. So this way you get dry density and water content of a single point. Repeat at another water content for each point on the curve. And that's basically, then you, every time you repeat that, you get another point, and then you connect those points to form the curve. Here, I should also mention, you shouldn't be reusing the same so don't reuse previously compacted material. So, because once you compact it, you are jamming some grains together, and then even if you try to mechanically break that apart for the next point, many grains will stick together in compacted form. So every time you do this, you will get a slightly increased density. So your curve will go up a bit, and because of the hyperbolic boundaries, it will go a little bit to the left as well. So you will basically, it will just like be, you are storing some of that compaction energy in the soil. So your first point will be on this green line, and then as you gradually reuse material, your points will go towards the brown curve here. So it is going to be an incorrect measurement. Of course, that is provided that you have sufficient material for this, because every data point requires like maybe 2.5 kilograms, at least 2 kilograms of material here. That is after getting rid of the coarse fraction. So usually, in order to run this test properly, you need something like a sack full of soil sample from the site. Okay, this basically covers it. I hope things will be much clearer once you go through the lab session related to this as well.